Now that we've fixed that, we start opening stuff. Hooray! And we have tablet duplication. Awesome. Okay, cool. So, yep, you guys are not off the hook today. So, haha, lucky us. Okay. Let's see. I want you guys to come up with the names for these guys just as like a little warm up for what we did yesterday. And how about we do what's a good one? Come up with names for those three. And I would like you to come up with formulas for the next three. So if I put, let's see. And let's see, how about we do... Okay. That should be plenty for us to start. So, go ahead, put your answers in the chat there. Let's see what we get. Sodium phosphide, huh? Sodium symbol is not Ca. And just so you know, Shane, you do not need to capitalize these. So, yeah, exactly. So just calcium phosphide, exactly. And so Shane got that from looking at his periodic table, presumably seeing calcium, or Ca is calcium, and the P is phosphorus, and remembering that we need to change the ending of our anion to make it ide. And here comes Kevin with all the answers, and Kevin, as always, has everything correct. That's great. Sodium sulfide, and barium chloride. So remember, we're always putting our metal first, our positive ion first, and then we are changing the ending of these to be ide, okay? Because anion names will change. So sulfur went to sulfide, chlorine went to chloride. Awesome. Alrighty, so going from formula to name is probably the easier way to do things, because you just need to find the elements and throw them on there. And it's perhaps a little more tricky to go the other way around, going from the name to the formula. So let's see what you guys can come up with. Very nice. So potassium selenide you guys got from understanding potassium in group 1, selenium in group 16. Remembering that these guys have preferred charges, and doing your crisscross stuff or doing your charge balancing to understand that we need 2 potassiums for that selenide ion. Great. Okay, so, and then again, you've got the same idea here. You've got MgO. That's perfect. So you saw Mg was in group 2, so it's Mg2 plus. Oxygen's O2 minus. All you gotta do, stick them together, and poof, we're done. Hooray. Awesome. Okay, so in that case, I'll teach you now how to, by the way, if there's any questions, go ahead and type them out. I'm just gonna keep going for now. If polyatomic ions are involved, we do not change their names. For example, if we were to take the sodium ion and the sulfate ion, So just remember, sulfate is going to be one of the ones on the list that I gave you guys. So there's two columns. One of them, it's like alphabetical by the name, and the other is alphabetical by the chemical symbol. So it's duplicate. So it's only, half as much as it looks like, right? So you would charge balance these as normal. And so you would get Na2SO4, and you would name this one sodium sulfate. Because this one is the sodium ion, this one is the sulfate ion, and since there is a polyatomic ion involved, we're not going to mess with their names, so it's just sodium sulfate. Hopefully not too crazy there. Alrighty, and we can go the other way around too. We can say something like calcium phosphate. And we can say, okay, well, we know calcium is Ca2+. We know phosphate is PO4 3-. And so we're going to encounter something here that is going to be a little bit interesting. If you were to charge balance these, you could see that your least common multiple is 6. You need 6+, 6- to cancel out, or you could crisscross. But we cannot write it this way. Because if we write it just like this, that's telling us that we have 3 calciums, 1 phosphorus, and 42 oxygens, which is not the case. So what we're going to do here is put parentheses around our phosphate to indicate that we have 3 calcium ions and 2 phosphate ions. And if we were to count all of those, we would distribute the 2 for both the phosphorus and the 4 oxygens. So in this, there would be 3 calciums, 2 phosphorus, and 8 oxygen. All right, if we wanted to see exactly how many of each atom were in there. Okay, so that's how we would interpret this. So anytime you have multiple polyatomic ions, we're going to use parentheses. Alrighty? So anytime that you're going to have more than one polyatomic ion, we are going to use parentheses. Alright, let me just check our list. Did I have hydronium on there? And, like, ammonium? Let's see. Where did I put this thing? Extra resources. I did. Good. Okay. So most polyatomic ions are negative, meaning their anions are going to be at the end. However, there are a few that are going to be positive. And in this case, this particular compound, we have 2 polyatomic ions put together. We have the ammonium ion and the carbonate ion. And lucky us, that's just going to be ammonium carbonate. Okay, and it's understood we have 2 ammoniums there to balance out the carbonate anion. Alrighty, so with polyatomic ions, nothing really changes. We just have different names here. So let's do a couple. And so the sooner that you learn those polyatomic ions, the faster this is going to go. Because if you're going to have to look them up each time, that can take a bit of time. So it would be a good idea to get through those. Okay? And how about we do strontium acetate? Alrighty, so what are we going to have here? someone give me some formulas. I'll go ahead, and since we have not necessarily had the polyatomic ion chart for very long, I'll go ahead and give you those for right here, just to speed things along, since we only have an hour here. Obviously, of course, potassium is K+, and strontium is Sr2+. Interesting. Okay, cool. I like that. One thing with that, Kevin, I'm not going to put the parentheses since we only have one peroxide there. We do not need the parentheses. However, I'll show you an example where we would put parentheses for peroxide, but it's not necessary for this one. So, because this is part of the polyatomic ion, and this one is from charge balancing. We're not going to mess with that. Yeah, no worries, Kevin. No worries. And just in case anybody's wondering, why didn't we just write KO? It's the same reason. We can never reduce the numbers that are part of the polyatomic ion. So you might be tempted to say, well, hey, look, that, 2 there is going to be, they're both 2s. Why don't we just get rid of them? It's because the 2 from oxygen is part of peroxide. So we're never going to have... So Shane, this is a polyatomic ion, so they have their own... you would just have to kind of memorize O2 2- as a separate unit. You typically do not have just 2 oxygens randomly coming together otherwise. So peroxide is special. So everything on the polyatomic ion thing, they have their own charges. So it's only when you're looking at the oxide ion that it's -2. Peroxide is O2 2-. Okay. Just again, in the interest of time, I'll go ahead and give us the formula there for the strontium acetate. Okay, so we want to use parentheses for the acetate because we're going to have 2 of them to fully balance out the +2 from strontium. Okay, and just to illustrate, Shane, if I were to, comparing these 2 ones, this one comes from K+ and O, then this guy here is oxide. That's our normal, just -2 one, right? This one comes from this, which is peroxide. So that is a different ion than plain old oxide. Okay, so that's why they're different. And just to really mess with you, there is another one, which is actually, interestingly enough, this one is O2-, which is superoxide. That's not one of the ones that I'm going to have you guys learn, but that's how you would be able to differentiate them. You know for sure potassium is +1, so you just kind of have to work with the rest of it to see. So, you're absolutely correct. Plain old oxide should have -2, but if it's a special ion, a polyatomic ion, there will have different names. Yeah, I know, that's the idea, right? That's chemistry in a nutshell. Makes complete sense and none at all. So, Perfect. Good. Then my job is done. I have completed that task. So I would not worry about this one because I'm not making you memorize superoxide. But that would be another example of a polyatomic ion that may confuse you. Alrighty. I think it's time to do a couple more. Do these three. Yeah, right. Brain explodes. Perfect. Alrighty, so very similar compounds here. However, these are very, very different in terms of their properties. So obviously all of these are sodium based, right? So we know that sodium will be the first part. So we need to basically now, sodium. We need to look at the anion part, right? So we know that this guy here must be ClO3 minus, ClO2 minus, and just Cl minus. So we could go ahead and reference our handy dandy periodic table, a chart of polyatomic ions. We'll go ahead and find their names. In this case, it may be easier to use the right column because that one has all the chlorine-based polyatomic ions organized nicely for us. All right, so I agree. This one is going to be sodium chlorate. This one is sodium chlorite, and this is sodium chloride. So, of course, we must make everything absurdly similar to each other, just to make things difficult for you guys. However, this is kind of where the aha! I got you, Kevin. There's no oxygen in the last one, so that would be just ClO minus. So it's plain old sodium chloride, happy table salt, right? So here's an example for us. Sodium chloride, table salt, not really harmful for us, of course, unless we just, eat a ton of it or drink, seawater or something for an extended period of time. But the other two, the sodium chlorite and chlorate, are both much more toxic to us, right? You probably know sodium hypochlorite is bleach. Chlorite and chlorate are even stronger versions of that. So if you imagine you're eating sodium chlorate, that's a very bad thing to do. So the names do matter. These are all different compounds, and getting them mixed up can be a very bad thing. So especially since a lot of you are going to healthcare, obviously you're not going to order someone, a sodium chlorite IV or something. It's something to keep in mind. Okay? So, naming important. Good stuff for us. Alrighty. Next. We have another whole section of metals that we haven't dealt with. I know you guys are aching to find out about the transition metals. And we're going to see that while stuff in, groups 1 or 2 or 13 or 15 through 18 or 15, 16, 17 all had fixed charges, most of the transition metals do not. For example, iron very often occurs as these two ions. Or something like chromium, which often occurs as, one of these ions. There's a whole bunch. Chromium also goes to 4+. It just depends on the environment that it's in or how it's been treated. And so we're going to see that we have to call these by special names because we can't just say iron anymore, since iron could have different charges. It just depends. However, we have a nice way of referring to this. We would say this guy is iron 2, and this one is iron 3. We just indicate the charge of the ion in parentheses with Roman numerals. And so, for example, this would be chromium. If I could spell chromium. We would say that's chromium 6. Or this is chromium 4. Okay, so we would there also are some old terms. I don't want to have you guys memorize them because they're really old, but they exist. Some people call this ferrous, and some people call this ferric. They exist, however, they're kind of getting to be more obsolete. Having the Roman numerals in parentheses is a more preferred way of describing the charge of a transition metal. And how we're going to do this is we're going to say, okay, look, we have, for example, we have two different compounds with iron and oxygen, so we cannot say iron oxide. Right? So we could say that for sodium and oxygen because those only make one compound put together. However, we cannot say that for this one. What we're going to have to say is, okay, we know that oxygen is 2-, right? And as a result, because there's the same number of irons as oxygens, this guy should be 2+. So we would call this iron... I'm sorry, let me write this on a different level. Iron 2 oxide. Yes, transition metals very rarely do have a negative charge. There are a very few examples, but I will show you one just to engage your curiosity. But most metals, 99.9% are going to be positively charged. So there's a very few number that can go negative. So again, we know that the oxygen here is -2. So overall, 3 oxygens means -6, which means that this whole thing must be +6. And since we have 2 irons, each iron is +3, right? So again, compounds must always be neutral. So we would say this one is iron 3 oxide. All compounds must be neutral. So, I mean, the whole thing, why we have... this one, sodium must be +1, and oxide is -2, right? So this one is neutral. However, this one here, +1 -2, does not work, right? This would not be the correct compound. It would not work that way. That's okay. That's okay. That's okay. No dumb questions. I understand we are going through a lot of different stuff, so we're okay. Alrighty, so when we have a metal that has a variable charge, meaning most transition metals, we have to put the a charge in parentheses. So I'll put that in purple. Most transition metals. We need to decharge in Roman numerals in parentheses. Oh, you want sodium superoxide, Kevin? That would be this. That would be sodium superoxide, since superoxide is O2 minus 1. Okay, and that, notice, is also charge balanced, right? Plus 1, minus 1, if it were superoxide. Okay, however, I'm going to delete this because people are just going to get confused, and we're going to just hide that. It never happened. Okay? Okie dokie. So, in that case, we can do a couple more. Let's see if we can do this one, and fluoride. Why not? So you guys are going to become experts at your periodic tables, by the way. Just doing all this naming, you will become very, very good at it. Okay, so remember, the 2 in parentheses for this first one means copper 2+. Alright, and sulfate, you remember from our chart, is SO4 2-. So putting these together, we would get CuSO4. Hopefully nothing too crazy there. Cobalt 3 tells us it is cobalt 3+. We remember fluoride is F-, so we would have to charge balance this like that. Oh, by the way, I did promise Shane that I would do one that had a negative metal. Again, not a common thing, but I am just feeding his curiosity. So, there are a few examples of something where you will have a negative metal. I'm not going to teach you how to do these because there are so few. There's not really a like a set of rules that we would use for them. This one would be called Cesium Oride. And in this case, gold is -1. So cesium is such a reactive metal that can even give an electron to another metal, like gold. Gold is particularly, I wouldn't say stable as a negative charge, but it is more like susceptible to getting a negative, or getting one more electron than most other metals would be. And this stuff, cesium oride, is like extremely explosive because it's not quite stable. So, yeah, don't worry about this. Also, I'll put this in parentheses. Okay, don't worry about that one. But that is just a, example of something like that. Again, not common at all. Alrighty, how about we do a couple more and then we'll move on to our next one. Goldide, I know, yeah. Because again, it's such a weird one. They call it by its Latin name, aurum, so they say oride. Go figure. And how about okay, so typically the anions, you are going to know their charge, right, for all of these. So we know that carbonate is CO3 2-. It is a carbon. Yeah, sorry, I know parentheses and C's look the same. I'll try and make that a bit more obvious for us. Let's erase that. Hopefully that's better. Yeah, I think that looks better. So, yeah, that second one is a carbon. At least with, like, if it's, like, typed out, it would be easier. Okay, so Satori, let's see. If I pop open our Discord here, it is here in the extra resources part of our Discord channel. There's this big old chart that I've put up that has all these polyatomic ions in it. So that's the one that we're going to be learning from. Okay, and so everything in this column is the same as this column. They're just organized different ways. So this is alphabetical by the name of the ion, and these are by the chemical symbol. Okay, so back to... No, go away. Okay, back to this one. Cool. So we know carbonate is 2 minus, right? So if we have 3 of them, that means overall this part is -6, right? Each carbonate is -2. 3 of them overall means -6, which tells us that our positive side must be +6. Remember, they always have to cancel out. And since we have 2 cobalts there, that tells us that each cobalt is going to be 3+. Exactly. So we're going to write cobalt 3 carbonate. Okay. So the hard part is just figuring out the charge. Other than that, we have to just... the rest of it's the same. Keep the metal name, keep your polyatomic ion name, or anion name the same way. Alrighty, so next one, we know chlorine has to be -1, right? And if we have 7 of them, -7, which tells us this has to be +7. Since there's only 1 manganese here, we know that's going to be 7+, right? So we would write manganese 7 chloride. Alrighty, so hopefully that one's okay as well. When you're dealing with polyatomic ions, you have to figure out their charge based on the compound that they're in. So remember, you could have cobalt being a whole bunch of different oxidation states, what they're called, different charges. So it just depends. There's no easy way for us to say, okay, yeah, cobalt's going to be 3+. Okay, cool. Questions on those? We do have 3 special transition metals. Which we may not even call them transition metals, but we're going to call them transition metals. Silver, zinc, and cadmium. I'm going to just make zinc happier here. These 3 have fixed charges. So unlike the rest of the transition metals, like iron or cobalt, which could have a whole bunch of different charges depending on what they're reacting with, silver, zinc, and cadmium do not ever change their charge. So silver will always be +1, zinc will always be +2, and cadmium will also always be +2. There is a kind of a way to remember this. If you have your periodic table here, I'm just going to write them down here. If you have your periodic table, you know you've got the rest of it going around and blah, blah, blah. Why is there no 7 after chloride if chloride only had -1? There is a 7 after chloride. It's right here. Poof. Oh, unless you mean in the name? chloride is always -1, so we don't need to put a special thing for that. It's understood from this that we have manganese 7+ and we have chloride -1. That's where we're getting that. Okay, hopefully that makes sense. Okay, so here's our special trick. Alrighty, so we know that aluminum is 3+, right? It's in group 13. If you want to do it this way, like they are diagonal next to each other, 3, 2, 1. If you just go diagonally down from aluminum, how does that work with it? Can you explain your question a little bit more? So, for example, you would just say this is zinc chloride. Because zinc has to be 2+, chloride has to be -1, so we would just make that ZnCl2. So these guys you could like treat as though they are, pretend they're like sodium or potassium or something like that. Where although they are technically located within the transition metal area, they only take 1 charge. So we do not have to worry about Roman numerals with these guys. So we understand that their charges are fixed. Just like how sodium is a fixed +1 charge, it does not change. It's exactly like as if we were to use sodium. So, you know, NaCl versus AgCl, sodium chloride, silver chloride. That's it. Easy. However, if we have a metal that is not one of these fixed charges, like this one, we would have to say iron 3 chloride. For their naming. So treat silver, zinc, and cadmium as if they were just like, you know, sodium or calcium or one of the other metals that has a fixed charge. Okay, and so you can look on your periodic table. Aluminum, zinc, and silver are like kind of in a diagonal. And so you could remember it, you know, aluminum is 3, 2, 1. If you just go down that diagonal. 3, 2, 1. So hopefully that would be one way to remember that. And cadmium just the same as zinc, so don't worry. Or same idea. Okay. We have 2 more things to cover, and I hope we have enough time. So, here we go. Non-metal, non-metal. This is how we're going to name these. These are the easy ones. Oops. One thing to note about these are not going to be ionic compounds. So previously the metal, non-metal ones, we had a positive and a negative thing stuck together because they're attracted to each other. With non-metal ones, these are not ionic. So we do not have carbon plus and oxygen minus or something like that. Not the case here. We're going to see later that these involve sharing of electrons instead of just giving them away. So we have different ways of naming these guys. And so you've seen these both before, carbon dioxide, carbon monoxide. These are the easiest easiest things to name because we just have to say the prefix, then the first non-metal. Always just do it in the order that you're given. And then another prefix, the second non-metal, and then the "ide" ending. Yeah, these are going to be covalent compounds, so we'll talk about those later on in the course. And the prefixes are going to be mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and we'll go up to deca. So that's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. Boom. Easy for us. There's only one more kind of rule here. We never start a name with mono. So even though there's only one carbon in both of these examples, we don't say monocarbon dioxide or monocarbon monoxide, because we understand if there's no prefix, there's only one. So just again, standard, we don't ever start a name with mono. So we just have to give. These are pretty easy. We see, okay, we have 2 sulfurs, so disulfur, and then trioxide. Easy. Tetraphosphorus, decoxide. Boom. These are the easy ones to deal with. I don't know. Throwing out more examples here. Remember, we don't start a name with mono, so we're just going to start with xenon. And then now we will do our prefix for fluoride. And same thing here, phosphorus, pentachloride. Easy, easy, easy. Yeah, I could do that. But look, it's right here. You'll have it in your notes. You could just come back to this thing. But yeah, I'll try and find one for you guys. I'll throw that up there. Okay, but these should be the easiest ones to name because it's just how many of each there are. That's it. Boom, done. Going the other way is not bad either. Tells us right here we have 2 sulfurs and 4 chlorines. Easy, easy, easy. Any questions on these? This part is easy. One thing to note, we are never going to use ditri or whatever with ionic compounds. That would again be our metal non-metal. Okay, we only use ditri, tetra, whatever with non-metal only compounds, covalent compounds. Okay, ionic compounds we do not name this way. Okay, a lot of you will fall victim to that. We must say that this is calcium fluoride. It is not this. Okay? I will yell at you a lot about this because I guarantee some of you will do it. So never, never, never use di or whatever if you have a metal, non-metal. Okay, cool. Since we just have a few minutes, I have to kind of zoom through the last part just to have it out there. We can finish practicing it on Monday, or Tuesday rather, but I gotta get this going. So I have avoided one particular element so far, and that is hydrogen. Hydrogen can either be H minus or H plus. And you'll know based on what it's with. With a metal, H is negative. H is going to be plus 1. So, for example, this one here is H minus because potassium is a metal, right? We would call this potassium hydride. And this one we're going to call hydrogen chloride. Okay, because hydrogen is plus 1, chlorine is minus 1. Some of you may think hydrogen is a non-metal. Why aren't we calling this hydrogen monochloride? It's because hydrogen is a special element. We will pretend it's a metal. So we are going to treat naming stuff with hydrogen as if it were a metal. So we could say also something like, we are going to call this hydrogen sulfide. Okay, we are going to treat it as a metal. Okay? And look here. This is actually just hydrogen oxide. You may have heard that thing long ago about dihydrogen monoxide. There's no need to do it that way because hydrogen we are going to treat as though it were a metal. Nobody says dihydrogen sulfide, it's just hydrogen sulfide. Nobody says hydrogen monochloride, it's just hydrogen chloride. Trust me. Don't believe everything you read on the internet. Cool. Alrighty. But it gets worse. You thought it was easy. Or maybe you didn't. But it gets worse. When they're dissolved in water, they act as acids. So we will name them as acids. We are going to illustrate this with a couple of examples. I'm going to give you a couple right here. This AQ that you see me writing here is aqueous, which means dissolved in water. So if we want to distinguish something as an acid, we will write AQ next to it to indicate that it is dissolved in water. And I will tell you the names of these guys. This one will be hydrochloric acid. This one will be chlorous acid. And this one will be chloric acid. So already your minds have been blown. You're done with chemistry. You are fiddling with the drop button on the chemistry course. Don't worry, it just takes practice. It is not going to be completely crazy. There are rules for this. Since all of these acids will have H plus as their positive component, we are going to look at the anion. And just remember, H is going to be H plus with all of these, so we'll get to that. Look at the anion. Okay, if the anion's name can be one of three things. Anions can end with "ide," with "ite," or with "ate." Right? "Ide" we saw was going to be our just regular elements typically, and then "ite" and "ate" are both polyatomic ion prefixes. So your acid will become whatever your anion name is. So that could be chloro or bromo or whatever it happens to be. That's where we're going to put the anion name. With this, it's just the anion name, us acid, and then the last one will be just anion. So will just be ic acid. Alrighty, so there are three basically different like classes of acids that we're going to have. So if we look at it, and notice that there's always going to be enough hydrogens to balance out your polyatomic ion. So we look at the anion. This anion is called carbonate, right? It's CO3 2-. We're going to see, what does this anion end in? Does it end with "ide," "ite," or "ate"? Yeah, unfortunately, Shane, yes, this is somewhat rote. But unfortunately, we have to have a systematic way for naming things so that we all understand them. And so it's just going to be like, for this part, it's just, it's rote. Unfortunately, there's nothing I can do about that. So, just rules to learn. Not concepts, just rules. So, sorry, nothing I can do there. Okay, so carbonate ends in "ate." So, that will be carbonic acid. All right, so we have gotten rid of the "ate," and we replaced it with ic acid. With this one, okay, this anion is Se2-, that is selenide. Remember, if it's just one element by itself, it typically takes the "ide" ending. And so we say, okay, if it's "ide," we have to put hydro at the start. And then we're going to put the part without the "ide," so selen, and then ic acid. This one here is nitrite. And I know this you guys are being like, what the hell, how do you know all these, how are we expected to know all these right away? This is where memorizing your polyatomic ions will become much more valuable for you, right? So understanding that NO2- is nitrite right away is very nice for us. So we see it ends in "ite," so that means this is going to be nitrous acid. Okay, so again, this is systematic. So you should always be able to find out what we're referring to with these. Let me give you a couple more examples. Let's go the other way. hydroiotic acid. That tells us, we say, okay, which one of these had hydroic acid? That's stuff that ends in "ide." So that tells us that this came from iodide. And so we're going to need to remember that iodide is the name for I-. And since we know all these acids will just be with H+, we're going to put H+ and I- together, which gives us HI aqueous. Okay, don't forget your aqueous for this part. Okay. Perchloric acid. So it looks like we have ic acid is our ending here. So we're going to go back up to our rules. Which of these is ic acid? Notice we don't have a hydro here, so just ic acid. So that tells us something that ends with 8. So we have perchlorate. We look at our periodic or polyatomic ion chart. We find out that perchlorate is ClO4-. Again, we need H+ in here. So we put these guys together. HClO4 aqueous. Yes, very nice, Kevin. Have I destroyed your brains yet? Do you guys still have like anything left up in there churning around? I wonder if this stuff will make you cry as much as sig figs. That's the real question. So we'll see about that. Okay, so we will practice more of these on Tuesday. I totally understand this is not... this will take practice. So this is generally not something that is very obvious to us right off the bat. So we will practice more. I did put homework up. You are welcome to start on that. That will be due next Sunday. So 10 days or 11 days or whatever it is from now. That's going to be more than 1 week. You'll have to practice with this. Okay, there are plenty of practice things available online also. Just like Google, like chemistry naming practice or something. You'll have plenty of it. So Tyler, you'll take a picture and submit it on Canvas. You'll either... I mean, if you can, print it out and then write on it and then take a picture and submit to Canvas. That's the easiest way for me. However, if you don't have a printer, you could just write your answers on like a separate sheet of paper, take a picture, and send that. You could scan stuff also. And then just submit on Canvas. You'll go on Canvas. Let's see. I guess I could just show you guys. Okay. Let's see. Is this gonna be... Yeah. Okay. So, for example, on these... Yeah. I don't have an announcement. You guys, if you're submitting something, you'll go here. Actually, I have to put this as student view. 1 sec. Okay. So, I'm gonna go submit my homework. What you're gonna do here is you'll click this Submit Assignment button up here. And you're going to go ahead and choose your file from wherever it is, and you'll just upload it and submit it, and that's all you have to do. Okay? So that's how that stuff works. Alrighty. So I guess I didn't publish this assignment yet for you guys. Oh no, it's right here. I just didn't put it in the thing yet. So you can see that you're gonna have... Oh, I can't preview it here for you guys. It's a... Fine, I'll just do it. Gosh, you guys make me work. Look at all this. Oh, how fun. Yay! Look at all of these. Hooray. Yeah, so go ahead, have fun. Knock yourselves out. It's exciting. Yay. Cool. Okay, so have fun with these. Yeah, fun with parentheses. So yeah, it'll be exciting. Yeah, right. No, not allowed. You're gonna have to do this in no matter what chemistry class you take anyway. So too bad. There is stuff that's gonna say here. So I did steal this from some guy named Dr. Mac. I have no idea who the hell he is or she. Um, but there are some ones that have like the old nomenclature. You could just skip those. I don't really care if you know, learn Stanic. That one is Tin 4 plus, by the way, but I don't need you to learn that. So if there's anything that's like, what the hell, we didn't learn anything about this, you can just skip those. So, or you know what? I guess I could write which ones to skip, so you guys don't have to think about it. Okay, I'll do that. Okay, well, whatever. You guys enjoy your weekend. See you on Tuesday. You do have two things that are due this upcoming Sunday, so don't forget those. But this particular one will be due next Sunday. Okay? I am gonna ping you guys in Discord with your like participation thing for the week, just to, because I have to, according to the state, do that. So, yeah, we'll have that. Okay. See you guys. Have fun. Enjoy. Take care, guys.